Okay. All right. Good morning, everybody. Can you hear me? Yeah. Okay. All right. Today we have 3 50-minute talks this morning. So breaks are 15 minutes. Just to make sure everyone knows, and then we can go ahead and get started. It's my pleasure to introduce Stephan Stadler, who's speaking about cat zero spaces of higher rank.
Okay, thank you. I hope everybody can hear me. So yeah, thank you for the invitation and the opportunity to present this talk, even though I couldn't come in person. I would certainly prefer to give this talk in person, but I'll try to do my best and present it online. Okay, so I want to talk to you about some rigidity results in zero geometry, but let's start slowly. So let's agree. So cat-zero spaces are geodesic spaces where whenever you look at a geodesic triangle, can you see this these drawings? Okay, nobody complains. I'm not quite sure. So whenever you look at the geodesic triangle and its comparison triangle in the flat plane, then you get the following estimates. So look at 2 points P and Q on your triangle, and then the corresponding points on the comparison triangle. Then the distance between those points in your space is at most the distance that you see in the Euclidean plane. And so for Riemannian manifold, for simply connected Riemannian manifold, we know that it is cat-zero if its sectional curvature is bounded above by 0. So this expresses a sectional curvature bound, but it's a global condition. It holds for all triangles, not only the small ones. And as a direct consequence, so geodesics are unique, cat-zero spaces are contractible, and so on. So triangles in these spaces, they look somehow slim. At least they can look slim. They can even look completely degenerate like this. In this case, we see like a branching geodesic, which would be the extreme case. And we somehow think of this as capturing some curvature. So if I look at a triangle that looks somehow slim, then it corresponds to a little bit of negative curvature. If I look at this completely degenerated one, I think of it as a lot of negative curvature. And of course, there also might be the other extreme case where we actually see a flat Euclidean triangle. And since those correspond to the extremal curvature case 0, they play a particular role. And so this, let me introduce this, this term flat, probably everybody knows. So a flat in my space is, I usually denote them by F, is a convex subset that's isometric to a flat Euclidean space of some dimension K. And of course, so formally speaking, a complete geodesic is also a flat. It's a one flat, but let's agree that when I talk about a flat, I think of something that's actually that sees actual Euclidean geometry. So K should be at least 2. And to get to one of the terms in the title, let us define what the rank of a geodesic and then of a cat-zero space is. So for a complete geodesic C, I can just ask, okay, what's the maximal dimension of a flat that contains this geodesic? And that would be called, right, that's the rank of this geodesic. And then using this, we can define what the rank of a cat-zero space X is. Well, I don't, so this works for any metric space, but I'm only looking at cat-zero space, and whenever I write X, I just think of a cat-zero space. So the rank of this space is the minimal rank that I see when I look at all geodesics in my space. And so for instance, if I look at a hyperbolic space, then there are no flats, right? So no higher dimensional flats. So the rank here is 1. Of course, the rank, if I look at Euclidean space of dimension n, the rank is really n. And just to have one more example, if I look at a product of hyperbolic spaces, maybe hyperbolic planes, then this rank is really 2. So every geodesic lies in a 2 flat that I get if I project this geodesic to the factors and then take the product of those geodesics, and there is no 3 flat. So it's really 2. And just because it appears in the title, let's agree that higher rank means rank at least 2. So that means every geodesic lies in some flat of some dimension, right? At least 2. And we just saw an example of, well, we saw 2 examples of higher rank spaces, namely Rn itself, where n is at least 2, and a product of hyperbolic spaces. Well, actually, we could take a product of anything that's geodesically complete to get a higher rank space. But there is more, and the most interesting examples are these model spaces. They come in 2 kinds. So there's symmetric spaces of non-compact type, and right, so they're also rank 1 symmetric spaces. But if the symmetric space is not negatively curved, then it's going to have higher rank. And there's a second kind, which is called Euclidean buildings. So I'm not going to define them, but I'll just tell you how to think of them. So remember, symmetric spaces, they're associated to certain Lie groups over the classical fields, the real numbers or the complex numbers. And in a similar way, Euclidean buildings can be assigned to, well, Lie groups over non-Archimedean fields, like the p-adic numbers. And well, it's not a perfect match. So Euclidean buildings, there's a metric theory of Euclidean buildings by Kleiner and Leib. And some of these buildings are completely asymmetric. So there is not a single non-trivial automorphism of them. And so they are not assigned to any reasonable group. But they originally appeared in Tits' study of algebraic groups, where he wanted to study them geometrically and constructed buildings where these groups act nicely. In any way, so in large dimensions, all these Euclidean buildings come from groups, and then in 2 dimensions, there's a bit more. But all these spaces are examples of Cat0 spaces of higher rank. And you don't need to know anything about either the left or the right side. So for the talk, it's enough to think of the following 2 examples. So for symmetric space, we just take a product of hyperbolic planes. And if you want to think of a Euclidean building, you can think of a product of trees. So make the trees non-trivial. So something like this is good enough. We don't want to think of the Euclidean plane on the right-hand side. And so why do I bring these examples up? So they are what is behind the motivation of this talk. And the talk is motivated by the following conjecture. It's, well, I'm not really sure. I think it's due to Ballmann, but it appears in a paper from 2008 by Ballmann and Brünn. And it claims the following. So if you have a locally compact and geodesically complete Cat0 space of higher rank, remember that means every geodesic lies in the 2 flat or higher dimensional flat. And then if there's enough symmetry, so here I just, it's a simplified version. Here I ask that there's a geometric group action. That means it acts properly discontinuously and co-compactly by isometries. So what you should think of is maybe the action of the fundamental group of a compact Riemannian manifold on its universal cover by deck transformations. So in this case, there is really only these model spaces. So you can always have a metric product. We saw this to produce higher rank, but apart from that, there should only be symmetric spaces and Euclidean buildings. So this is why it's called rank rigidity, I guess, higher rank rigidity. So the conjecture is, in this form, is completely open, but there are a couple of known cases. And I guess the most famous one is the one for smooth Cat0 spaces, so for Hadamard manifolds. The first proof, I think, is due to Ballmann, and then shortly after, there's an alternative proof by Burns and Spazier. Both use intensively the structure result that was obtained earlier by Ballmann, Brenn, and Eberlein. And then there's this result by Eberle and Heber, which is not really, it's the same proof. What they do is they find a clever argument how to reduce the symmetry assumption from, well, Ballmann had it by, so the first two were for Hadamard manifolds that admit finite volume quotients, and then they reduced this to what is called the duality condition. But let's not get into this. But there are some known results beyond smooth spaces. And the first one I want to mention is for Euclidean complexes of low dimensions, Ballmann and Bryn were able to prove this rank rigidity result. So, but let me be a bit more precise. I just wrote Euclidean. So that means you have a simplicial complex of dimension at most 3. And then the metric you put on this is the flat metric on each simplex. And then you ask that this space is cut 0. This is something that you can read off the vertices. And then this metric, if this metric is higher rank, then it has to be rigid. So either product, so you have to split off a tree in low dimensions, or it is a Euclidean building. And there's one more result I want to mention, which is somewhat important in group theory. So for finite dimensional cube complexes, the result is also true. Here again, so cube complex is something similar than a simplicial complex, but it's made out of Euclidean cubes. And again, the metric is somehow determined. So on each cube, you really put the flat Euclidean metric. And then you ask that the induced length metric is cut 0. And then for such spaces, you know that if it's higher rank, then rigidity holds. But since Euclidean is so irreducible Euclidean buildings, they don't carry cube complex structures, or this metric is not a cube metric. It really says that this is a product result. So if it's higher rank, the space has to split. Okay, so this is about higher rank spaces, and the title says cut 0 spaces of higher rank. Nevertheless, there is accompanying conjecture and results for rank 1 spaces, which I want to mention for completeness. So, which is called the closing lemma, and will be clear why in a second. So again, in the same paper, so they conjecture the following thing. So if you have a locally compact and geodesically complete cut 0 space, and this time of rank 1, so that means there is a geodesic which does not lie in a 2 flat. Then again, you need the same symmetry assumption. Suppose there's a geometric group action, then this rank 1 geodesic is, so there is not only one rank 1 geodesic, there's even a periodic one. And then if there's one periodic one, then they're actually dense. So in this sense, this rank 1 geodesic somehow represents a hyperbolic behavior that spreads somehow throughout your space and is seen by the group. So if you put this together with the first conjecture, the higher rank rigidity conjecture, this really becomes a conjecture in group theory, because if you put these things together, then the rank condition can be attributed to the group, and then that would then have some applications in group theory, but I don't want to get into this. Let me just mention that also this thing is known in a couple of cases. And the most important one, I guess, is the smooth space, is again Hadamard manifolds, and that's even earlier than the rank rigidity theorem. This really goes back to Berner's thesis. And then also Ballmann and Bryn tried to prove this in the singular case, but notice that here they only managed to do it in dimension 2. So the rigidity part was done up to dimension 3. But this closing lemma is even open for 3-dimensional simplicial complexes, which is right. This is somehow shows that we really don't understand this. But there's a third case, namely the cube complex again. So Capras and Segev also proved really both sides. So then you have this dichotomy: either it's rank 1, then you see periodic rank 1 geodesics everywhere, or it's really a product. Okay. So now let me come to results. Here's Theorem A, and all the results are for higher rank spaces. I do not know anything new about this closing question. So theorem A says, okay, so this is the same assumption than in the conjecture. You have a locally compact and geodesically complete cut-zero space of higher rank, some rank n. And suppose you have a geometric group action. But then I need to ask something more. Sorry. Now suppose this space contains a periodic n flat, and I'm going to tell you what that is in a second, but no n+1 flats. Then the conclusion holds. So let me tell you first. So an n flat is an isometric embedding of Rn. So it's periodic if its stabilizer basically contains Cn acting by translations. So what you should think of, in the quotient, you find a torus. And so this no n+1 flats, it's more or less a question of, is this rank well defined, yes or no? If you think of symmetric spaces, then you could define this rank differently, right? It's not only the fact, so if you have a rank n symmetric space, then every geodesic lies in an n flat, but there is no n+1 flat. So in this sense, so this rank is really well defined. And what we define for general cut-zero space is more like an inequality. So we say a space has rank at least n if every geodesic lies in an n flat. But in general, it actually happens that you could have a space where almost all geodesics lie in no higher dimensional flats, but there are higher dimensional flats. And part of this rank rigidity statement is that if you have higher rank, then a mixture of top dimensional flats can only appear if the space splits. And this is actually a completely non-trivial statement. And okay, so let me just say something about this additional assumption. So this periodic flat, the assumption that periodic flat does not appear in the conjecture. So I want to comment if it's reasonable or not. I think it's reasonable, but it shouldn't be there. And why is it reasonable? So if you look at a model space of rank n, so say a symmetric space of rank n with a geometric group action, then actually the periodic n flats, and here it should really say gamma periodic n flats are dense in the space of all flats. So it's not only one that closes up, but almost every flat closes up. And actually for smooth spaces, this is known to hold. So the existence of a periodic flat is known to hold even without the rank rigidity theorem. So that was proved before the higher rank rigidity theorem was proved. So in a sense, this recovers the smooth rank rigidity theorem, but so cards on the table. So in order to prove this, the existence of this periodic n flat, they're all right. They establish so much structure so today it's not really hard to go from what they have at that point to the rank rigidity theorem. So it's not. I wouldn't. I wouldn't say it recovers it. Okay. So So then I want to tell you about two more theorems, and both of these theorems kind of try to push this theorem A a little further and get rid of some of the flaws that are in there. And flaws meaning something that, doesn't appear in the original conjecture. And the first flaw is this periodic. It doesn't say anything, so the conjecture doesn't assume anything about periodic. So here is what I can do. Theorem B. So same assumption, but now I have to restrict to rank 2. And then I don't have to assume this periodicity. So if you have a space where every geodesic lies in a 2 flat, but the space does not contain any 3 flats, then the conclusion holds. So, so it has to be a model space, so a symmetric space, so Euclidean building, or it splits as a product. And concerning the other flaw, namely this requirement that the rank is well defined, that there is this lower bound and the upper bound agree. Here's theorem C. So again, same assumption than in the conjecture. Now we have some rank n, and okay, so there's a symmetry assumption. Ignore it for a second. Then the important part is now I asked that there's a periodic what is called Morse n flat. I'm going to tell you in a second what it is. Then the conclusion holds. So let me try to explain. So periodic flat, I told you, a periodic n flat is Morse if it doesn't bound a higher dimensional half space. So if n is 1, then a periodic 1 flat or geodesic is one that, you know, you have this this element acting co-compactly on it, but there is no flat half space. So the general thing, so if you have F, a periodic n flat, then the condition that stands behind this Morse is that there is no, say F has dimension n, then there is no half space of dimension n plus 1, which bounds this F. This would be asymmetric to something like array times some Rn. So in a sense, this periodic n flat feels as if it's top dimensional. Okay, that's somehow this periodic n flat feels fine. It's top dimensional, and then all the rest should follow the geometry that's seen by this periodic n flat. And then there is this this strange symmetry assumption. Okay, so acting co-compactly, I think everybody understands. But then there's this duality condition, and I don't want to get into this. It's just so for smooth spaces, if you have a geometric group action, then it's automatically satisfies this duality condition. It comes out from the fact that we have a nice measure preserved by the geodesic flow for smooth spaces, but there is no such thing for singular spaces. And it might be true that it's actually, I think it's conjecture that every geometric group action satisfies the duality condition, but I don't think that there's even a partial result in this direction. So I just have to assume it here. But then we get the conclusion without asking a priori that that the dimension, that this, say, lower rank is equal to this upper rank. So here I do not ask, so every geodesic lies in an n flat, but I do not ask that there is no n plus 1 flat. And there could be an n plus 1 flat, right? So we could just take a product of two cut-zero spaces where one of them is a relatively hyperbolic space where you have hyperbolic geodesics everywhere, but then there's some isolated higher dimensional flats. And if you take a product of this with something else, anything else, you create a higher rank space. This higher rank space, right, falls into this theorem, but not in Theorem A because of this, right? So because of existing geodesics of different rank. Okay, so these are all the results I want to present. So maybe I stop for a second. Are there any questions on formulations or any comments? It's rather hard for me to see. Just interrupt me and make sure I notice.
We do have a question.
Okay, perfect.
Hi, Stephan, Ricardo here.
Hi.
Hi. In Theorem A, can you maybe go back? I think it was Theorem A.
Yes, let me go back.
Right. The assumptions about having a periodic n flat, so gamma periodic, right?
No,
I'm wondering...
Thank you. No. So actually, it's the formulation is a special case. I didn't want to. So I also don't need the geometric group action here. All I need is that, I mean, well, I'm just gonna say it. So I need that the dimension of the Tits boundary is n-1. So if you have a geometric group action, this follows from a fundamental result of Bruce Kleiner. And I just didn't want to mention the Tits boundary at this point. So I kept this there. And the periodic flat has to be periodic with respect to the full isometry group. So there is no, you don't need a discrete, yeah. I think that's the answer.
Oh, okay. So as stated, though, if you have a different geometric action, the n-flatted was periodic with respect to one of them, like you would still have a one
Yeah,
that's
then-
periodic with. Okay, it
Yeah,
doesn't
then
matter.
you're good. Yeah, if you find any geometric, right.
Okay, got it. Okay, so it doesn't depend
So-
actually on that action. Okay.
Um,
Okay, but you're going to explain
I also
more
think,
about it. Right?
Actually, the formulation here would be fine to just say, right, so the dimension of the Tits boundary should be n-1. So that implies that there are no n+1 flats. But then you could just ask, there's Zn in the isometry group. That would be good enough.
Okay. Okay, got it. Yeah, thank you.
Are there any more questions right now? Looks good.
Okay, then let me continue. In order to say, well, yeah, just try to avoid it, but here we are. In order to say something about the proof, I need to tell you what the Tits boundary of a K0 space is. I guess most of you know, but I try to keep it light so you can follow, even though you already know. So, so the Tits boundary is a space that you can associate to a K0 space at infinity. And let's begin slowly. What you usually do is first you associate what is called the ideal boundary. And its definition, usually you denote it something like this. So del infinity of x. And as a set, this is, so geodesic rays, so up to finite distance. Let me just write it like this. So up to finite, maybe the h is for Hausdorff. So you look at a geodesic ray in your space, and then if you see a second geodesic ray in your space, which is at finite distance, then what you think of it as representing some point at infinity. And okay, that's a set. And then it's not really hard to see that whenever you have an equivalence class representing a point in this ideal boundary, then you can pick a point, a base point, maybe P in your space, and you actually find a geodesic ray based at this point representing this class. So you think of it as being asymptotic to the same point at infinity. And then you can put a topology on this by asking that pointed rays converge point at Hausdorff. So a sequence of points at infinity, they converge to another point at infinity if these rays, actually, if you fix the base point P, then the geodesic ray representing this class is unique. So, and then convergence means that these based rays at P converge. And this is what is called, right, this is what is called the ideal boundary. And let's see what these ideal boundaries look like in simple cases. So for a Hadamard manifold, right, which is diffeomorphic to Rn, the ideal boundary is homeomorphic to the sphere of one dimension less. And why is that the case? So if we fix any base point, maybe P, and then, right, so it's a manifold of dimension n, the space of directions is just an Sn minus 1, and we can look in some direction, and since there's no branching, our M was a smooth manifold, we can just associate this unique geodesic ray in this direction, and the map that assigns this direction to the corresponding ray, that gives you homomorphism between the ideal boundary and this space of direction, which is homomorphic to Sn minus 1. So, but of course, I mean, for a general K0 space, this can be something else. So think of a tree, and we'll see some, maybe a Cantor set at infinity. But okay, so this is the first thing I wanted to introduce, and now there is a natural metric on this ideal boundary, and it's usually called the Tits angle. And sorry, okay. And it's defined as follows. So what is this? So I take 2 points at infinity, and then I pick a point in my space. Then there are arrays representing those 2 points. And then at this point P, there's a well-defined angle between the corresponding directions. And the Tits angle between those points is just the largest angle I see within my space. So for every point, I look at those 2 points at infinity, I measure the angle at that point, and then I take the largest one I see. And this definition is not very good for proving anything, but it is a definition, and it's good enough to understand simple examples. So let us try to figure out what the Tits boundary of some simple spaces is. So the first example is the Euclidean space. So, okay, so first of all, I should say that usually I denote the Tits boundary by this, so partial Tx, and for short, this is, as a set, it's this ideal boundary, and you equip it with this Tits angle metric. And it's a fact that this space is cut 1 always. And okay, and now let's turn to the example. So the Tits boundary of Rn is, well, I claim that it's the round sphere. And the same map that showed us that the cone, the ideal boundary of Rn is homeomorphic to the sphere, shows us now that the Tits boundary is isometric to the sphere. Because let's see. So I take 2 points at infinity in Rn. Maybe this point and this point. And then let's represent it, or let's look at them from different points. But if 2 geodesic rays in Rn are at finite distance, then they're actually parallel. So it means that if I change my base point, the angle doesn't change. Okay, so in order to measure this Tits angle, I can just fix the base point and measure every angle there. And measuring this angle is just the angle I see in the space of directions. So that gives me this isometry that's claimed here. But that's, of course, it's an extreme case because Rn is flat. So let's go to the other extreme and look at a hyperbolic space. Sorry. And I claim that the Tits boundary of a hyperbolic space of any dimension, let's say 2, is discrete. And why is that true? So if you look at the hyperbolic plane, and then let's pick 2 points at infinity, what we are looking for is the largest angle we see those 2 points, but I'm sure everybody knows. So for any 2 points at infinity, we actually find a geodesic connecting those 2 points. Then if I place myself on this geodesic, the angle I see between these 2 points is pi. So that means any 2 points have distance pi. So the Tits metric on the hyperbolic space is discrete. And now kind of the air already gets thin. So there's one more thing I can discuss, and then every other space, either we don't understand the Tits boundary at all, or it's the Tits boundary of a symmetric space, and that's already quite a complicated discussion. So let me just close this discussion of the Tits boundary with one more example, which is good enough for the rest of the talk. And it's the Tits boundary of the product of the real line with a hyperbolic plane. So first of all, as a set, or with respect to the cone topology, we see a 2-sphere. So I'm not going to write anything. I'm just going to draw what it looks like and try to describe it in words. So we see a two-sphere, but then we have this much finer topology coming from the Tits metric. So how does it look like? I claim it looks like this. So there's one bad point here, if you will, and there's another bad point down here. And those correspond to the ideal boundary points of this line. So there's a general fact that the Tits boundary of a product splits as what is called a spherical join of the Tits boundaries of the factors. So this would be something like this, R join H2. So, and okay, let me see. So I can maybe try to draw this. So there are these 2 points. Right, so the Tits boundary of R is just the 2 points at infinity. And then the Tits boundary of the hyperbolic plane, we just figured that out. This is a discrete circle, which you would see somehow here. And a join between 2 points, well, you join every point with every other point, and then it's a spherical join if you put length pi/2 on each of these intervals. So let me make sure you understand this picture. The picture I drew is a one-dimensional space, right? In any reasonable sense, one-dimensional space, and it foliates S2 away from north and south pole, and all these intervals, they come together at the north and south pole. So if I want to walk in this Tits metric, I have to walk along these paths. And well, so I mean, it's not a locally compact space because of those 2 bad points, but away from those 2 bad points, it's really nice. It's a one-manifold. Okay. And a similar, well, slightly more complicated, but similar structure you see at infinity of a symmetric space. The term is a spherical building, and it is a certain simplicial complex where you have regular points and then a rather restricted pattern how these things interfere. Okay, so why did I introduce this? Because that's the key notion to prove theorem A through C. And now it's not proof from scratch, so I have to use several deep ingredients. So let me tell you what those are. The first is a theorem of Leib. I'll try to, so I think that's too much information. Let me just paraphrase what it says. So if you have a cat-zero space, well, locally compact and geodesically complete, if the Tits boundary looks like the Tits boundary of a model space, then your space is a model space. That's how you should think of this. But then I just described the Tits boundary of a rather simple space and then claimed that somehow the Tits boundary of symmetric spaces looks so and so. What the Tits boundary does is somehow capture the intersection pattern of top-dimensional flats. And if you think of an irreducible symmetric space, that's still rather complicated. So in order to apply this theorem of Leib, you have to recognize the intersection pattern of symmetric spaces. So that's right, that's still too hard. So we need more help. And there is this result of Alexander, which recognizes when a cut-1 space is a spherical building. So spherical building, just take it as the Tits boundary of a model space. And this reduces the task to find in this particular set. So let me explain what this set really is. So he says that any cut-1 space will be a spherical building if you find this particular set. It's supposed to be closed and it's supposed to contain all antipodes with every point. So I just show you the set in the example that we just looked at. So if we have the Tits boundary of the line and the product of a line and the hyperbolic plane, it looked like this. And there are 2 special sets. I already drew them before. Let me redo it. Coming from the 2 factors. Now, if you look at the north and south pole, and remember, so these half circles actually have length pi. So you call two spaces in a cut1 space antipodal if they're distanced at least pi. So in this metric, the north and south pole, they're antipodal, and they're the only antipodes. So if you take the set north and south pole as this two-pointed set, then it satisfies all the conditions that you see in Alexander's theorem. So it's a closed set, and it contains every antipode with all of its points. And what he claims is that whenever you see a cut1 space, which is geodesically complete, that's kind of the flaw in this theorem, and you find this set, which is closed and closed under taking antipodes, then the only way is that you look at a spherical joint or a spherical building. So, I mean, when these two results were out, so 2005, it's kind of clear that in order to prove rank rigidity, you want to combine them. So what you're left with is finding this closed set. And I do apply both theorems to prove theorem A and B. So let me maybe explain where this closed set A comes from. And again, I kind of try to convince you with this picture. So the picture we're looking at, as I said before, away from these two bad points, we see a one manifold. So this one manifold, and the complement of this one manifold I just told you is a set that we're looking for to apply this result of Alexander. And so you can kind of try to do the same thing in general. You try to find regular points, and then the complement of the regular set will hopefully be such an antipodal set as required by this result. And that turns out to be exactly true. And and Alexander probably, I mean, he knew that's the way how to do it because he conjectured. I mean, it's not in writing, but he claims that he talked to a lot of people around 2005, 2006 and tried to get them interested in this conjecture. So it says the following: so if a locally compact cut-zero space with a geometric group action, then the Tits boundary cannot be completely terrible. So there has to be one regular point. Okay, regular point means manifold point. So there's a neighborhood that's homeomorphic to an open set in Rn. And remember, so I claim that this Tits boundary is always a cut1 space, but it's never locally compact. Well, it can be the boundary of Rn, but apart from that case, it's never locally compact. And then there's this other flaw that's usually never geodesically complete. But if you think of this as a conjecture about cut1 spaces, so if you have a cut1 space, you can ask, well, does every cut1 space have to have a regular point? And the answer is no. So if it's locally compact and geodesically complete, then the answer is yes. And that's kind of the starting point of the structure theory of cut1 spaces. But for a non-locally compact cut1 space, it's just wrong. So somehow being the Tits boundary of a cut-zero space and then having enough symmetry to relate the Tits boundary to the geometry inside should allow you to find this regular point. And I couldn't do this, so it could still be true that you have a cut-zero space. So this might still be wrong. So you could still find a cut-zero space which is locally compact and has a geometric group action, but the Tits boundary of the thing looks like an R tree. We don't know how to rule this out, which is somehow absurd. But here is a result which goes into this direction, which is the starting point for theorem A through C, and it's a contribution to this regular point conjecture. And it says the following: so if you have a locally compact cut-zero space, and there exists a single periodic Morse flat, then there are regular points, and they appear in the Tits boundary of this flat. So let me remind you what these notions. So a periodic flat, again, is a flat. Sorry, somehow I changed color. So you have this stabilizer, so you have Zn in the stabilizer of this F, and stabilizer with respect to the full isometry group, and this F does not bound a half sphere, right? So F does not bound a flat half space. So that's what's behind this these words periodic Morse flat. And once you have that, then the Tits boundary contains regular points, and it's actually much stronger. So we already know that Tits boundary of this flat is a round sphere, and this round sphere will actually resemble what you expect, namely a Coxeter complex up to things of lower dimension. And now I didn't really explain how these things fit together, but let me just wrap this up and kind of try to say how it fits together. So the assumptions of theorem A through C all require this periodic Morse flat. So in A and B, it's just hidden by asking something stronger, right? If there's no higher dimensional flat, then you can show there cannot be a higher dimensional half flat if there's a geometric group action. So all these things rely on this theorem D. And then to prove A or B, you take these regular points, you look at the complement, which is then, well, you can then show this is a closed set, it's closed under taking antipodes. And then for theorem A and B, you can apply Alexander's result. And and then you can apply Lieb's result to get the full rigidity. And I don't think I can say something about this proof of theorem C. So I think I just finished in time, and thank you for your attention.
That was great. Are there any questions? Any more questions for Stephan? That n in theorem D is the rank. Is En action, is n is the rank?
No, so theorem, sorry,
dimension.
so I should have made this. So this theorem